We're moving on now to discuss RC circuits. Now, as they'd sound, R is for resistor and C is for capacitor. So, with an RC circuit, what we're really talking about is the discharge of a capacitor through a resistor. And that resistor isn't necessarily a resistor as such, but a source of resistance. It could be hooking up a capacitor to a bulb and making that bulb flash. What we have with our capacitor is some initial charge, as we said before, of plus Q on an upper plate and negative Q on a lower plate. These zeros merely indicate that this is an original charge of the totally charged capacitor. The capacitor, when connected to a resistor with a switch, so the switch is open, you hook a capacitor to a resistor, close the switch, the current or charge, as it will be set up, so the charge will flow out of the capacitor into the resistor. This will create a potential difference across the capacitor that will change. The potential difference across the capacitor is initially V0, which is the amount of initial charge Q0 divided by the capacitance C. Close the switch at t equals 0, the potential difference gets set up across the resistor, and that will cause the current to flow. So the initial current when you close the switch, right when you close the switch, will be I0, which will be V0, the initial voltage divided by the resistance, or Q0 over RC, hence the name an RC circuit. What we quite often care about when we have capacitor that is holding charge, I should say, is how long that charge will take to flow out of the capacitor and into the device of interest. If we have a flash bulb, we want to know what order of seconds, for instance, that flash bulb will light for. We don't want it to stay on for too long, but on the other hand, we want it to be on long enough to give us a good flash to get our photograph. So, if we do a little bit of derivation using calculus, which you don't have to do, we'll actually get an expression for charge with respect to time. And that's Q at some time t, as given by this equation. Now, the charge on the capacitor will fall off exponentially. That's, the base of the natural log. So, your charge at some given time t will be Q0, whatever your original charge was on the capacitor, times e to the negative t, this is the time that you're interested in, be it 1, 2, 3, 4, however many seconds, divided by resistance times capacitance. That is equal to the original charge times e to the negative t over some time constant. And this is very similar to the kind of constant you might see with something like radioactive decay. And it behaves in a very similar way, in that tau here, this tau, so this is t over tau, this tau is the time taken for 1 over e of the charge from the capacitor to flow off. So tau is the time taken for the charge to drop to 1 over e of its original value. And tau is R times C. And that's known as the time constant. So after t equals tau has basically passed, the charge is going to drop to Q being Q0, the original charge, times e to the minus 1. That'll be 0.37 times Q0. So this is how much charge you would have left after a t of 2 tau. So that means the charge then would be Q equals Q0, e to the negative 2 would be 0.135 Q. This should be subscripted 0, etc., 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 for however many values of tau you have. After a great deal of time constants have passed, eventually you should have a charge which approaches 0. That's an exponential decrease. So here's what will actually happen if you hook up a capacitor to a resistor and then discharge through it. Your charge, Q, starting out at Q0 here at some high value, will flow off of the capacitor and then diminish in an exponential fashion until it's almost reaching 0. This is one of those relationships that never really reaches zero, but effectively gets close enough to behave as it's zero. So you'll never actually see this cross this axis down here. And the rate of charge loss is proportional to how much charge you've got, Q. So that's Q on the capacitor versus T. Switch is closed at T equals 0. Here's T equals 0 here. And tau equals RC is the time taken for Q to decrease by e to the negative 1 times Q0, which would be this value here. So the decrease in the charge on the capacitor is very similar to the decrease in the amount of water you have in a bucket. If you drill a hole in that bucket, the water will run out of it. And the rate at which the water flows out is proportional to how much pressure you've got in your bucket. The more water you've got, the higher the pressure, the more will flow out. So the higher the Q you have, the quicker you will expend your charge, and the greater I will be for a shorter period. So when we're looking at an RC circuit and we discharge our capacitor, we start off with a high amount of Q, a high amount of charge, and that charge diminishes with time. That means the current, which is basically Q over T, how much charge is moving per time, where time here is RC, will be I0 is Q0, however much charge you've got, divided by RC, which is also V over R. Remember, this is Ohm's law. I is V over R, is also Q over T, which is Q over RC. That means as charge diminishes, current will start out high and also diminish by the same relationship. So the I graph versus the Q graph looks pretty much the same. And there it is. Your I versus T graph will give the same shape as your Q versus T graph. If I decreases at a constant rate equal to its initial rate, it would probably reach 0 after 1 tau and follow this dashed line, but it never does. It will follow this exponential line here. So let's take a look at an example. So in this example, we have a 4 microfarad capacitor. It's charged at 24 volts, and then it's hooked up across a 200 ohm resistor. What we want to know is the initial Q on the capacitor, initial charge, so Q0, the initial current, remember the font, through the 200 ohm resistor, what's the time constant, what's the RC value, and what is Q on the capacitor after 4, and this is milliseconds. So part A. We've got a 4 microfarad capacitor charged at 24 volts and connected across a 200 ohm resistor. So the initial charge on a capacitor will be Q0. That's C times the original voltage, which is 24. So that will be Q0 is C times V0, or 4 times 10 to the minus 6 farads, remember to convert them, don't take your micro for granted, times 24 volts. That will give you 96 times 10 to the minus 6 coulombs, or 96 microfarads. Part B said, the initial current here through the 200 ohm resistor, what is it? 4 microfarads again, 24 volts, 200 ohms are what we have to play with. Our initial current is V0, our initial voltage, divided by the resistance, which will just be 24 over 200, which will give you 0.12 amps. Yet there's more. Part C wanted to know what is the time constant. Well, again, same situation, but the time constant is given by tau, which is R times C. You've got your 200 ohms, you've got your 4 times 10 to the minus 6 farads. That will give you 800 times 10 to the minus 6 seconds. That can also be re-expressed as 0.8 times 10 to the minus 3 seconds or 0.8 milliseconds. So, remember, this is milli and micro that we're dealing with. Make sure you've got your prefixes correct. Finally, the last part of our question Said, what is the charge remaining on the capacitor after 4 milliseconds? Well, this is that equation we just discussed, where Q, how much charge we've got, is equal to Q0, the original charge, times e to the negative tau over t. We already found Q0 from our previous calculations, so this becomes 96 times 10 to the minus 6 coulombs times e to the negative 4 milliseconds over the 0.8 milliseconds we calculated in a previous part of this problem. That reduces down to 96 times 10 to the minus 6 times e to the negative 5. If we do that, we will get 0.65 times 10 to the minus 6 coulombs. So 0.65 microcoulombs will remain on this particular capacitor after 4 milliseconds, or 4 times 10 to the minus 3 seconds, when it started out with 96 times 10 to the negative 6 coulombs. You could, of course, figure out how many electrons this was by dividing by 1.6 times 10 to the negative 19 if you wished. So we've talked about discharging a capacitor. What about charging a capacitor? So if we charge a capacitor, our circuit will charge up, the switch will originally be open, we will close the switch, and then we will end up with charge flowing onto our capacitor. You can use what are Kirchhoff's laws, which we will also discuss or have discussed, and calculate the voltage drops across your capacitor system if you wish. Remember, this is electromotive force, this is V, the voltage, this is the resistance, this is the voltage, and this here is the capacitance. Or the voltage minus Q over C becomes 0. So here's what it typically look like. Here's a resistor, here's our battery source, here's a capacitor. You charge it up with the switch closed, open the switch, and leave charge sitting on your capacitor. So what happens when we charge a capacitor? Well, at time t equals 0, we're assuming the charge on the capacitor is about 0. And the current is going to be I0, which is the electromotive force from the battery divided by R. So V over R, but this is the battery's EMF. Q will reach some maximum value, Q final, when it's equal to C times the voltage of the battery. Remember, your capacitor always adopts the voltage that the battery is giving to it. A 9-volt battery gives you 9 volts across your capacitor plates. So when the current, which is the charge flowing on the capacitor, becomes saturated, the current will gradually slow down. The charge per unit time deposited onto the capacitor will slowly reduce. Well, I say slowly, it's on the order of milliseconds in this case. Will reduce and eventually stop because the supply has reduced as the charge builds up on the capacitor. So at time t equals 0, the charge on the capacitor is 0, and I equals I0, which is essentially V over R for the battery. Q increases, the current decreases. And there's what your graph will look like. This is not what people usually expect, because the current is, this is an epsilon here, this is the electromotive force divided by R times e to the minus t, or tau, over RC, which is I0 e to the minus t over tau. Sorry, t over RC. So what people usually do is put these two graphs together, but here I0 is identical to the charging case. Sorry, to the discharging case. This is the charging case. The discharging case, remember, Q went down, so I went down. In this case, the current starts off high and then diminishes. The current slowly falls off with time in this exponential fashion. But that doesn't mean that Q is going down. Q is actually going up. So we're starting at t equals 0 with a capacitor with no charge on it, and then the charge slowly builds. I say slowly because of this relationship, but the charge builds on the capacitor, eventually reaching some saturation point Q0. That means current starts off high and goes low, but Q starts off low and goes high. So just keep these graphs in mind. What does a QT graph look like compared to an IT graph for a charging case? What does a QT graph look like compared to an IT graph for a discharging case? And the only difference really is the QT graph. The QT graph has an exponential increase. I versus T has an exponential decrease in both cases. And that's what we're really talking about with the charging of a capacitor. Q starts off low and eventually saturates, filling the plates, resulting in a reduction in current, both of them exponential. One an increase, one a decrease. So we're going to switch gears a little bit now, and we're going to talk about RLC circuits. So we're throwing another letter of the alphabet in here. We're not really going to deal with these, as this deals with time-varying magnetic fields that really come about through an understanding of calculus. And we don't really want to get into calculus, it's outside the mandate of this particular class. But for an RLC circuit, what we're talking about is storing charge on a capacitor in this fashion. So here we hook up our battery to our capacitor and store charge in it. Then we'll take this switch and flick it from point A to point B. That will cause electricity to flow from the capacitor very quickly through this L. And what this L is an inductor. And what will happen here is this will generate, as the current moves through it, a little bit of magnetic field. And as the magnetic field is generated, it'll give back a little bit of current. So we'll actually wind up generating current from this coil in here, from this inductor L. And that's where we're going next, talking about generating current and talking about the induction of a magnetic field. And that's what an inductor does. Now, I just said we get a bit of current back when we do this. When we run current through an inductor, we'll actually generate a bit more current and generate a magnetic field. That doesn't mean we're violating conservation of energy here, because in the circuit there's some resistance, and energy is lost to internal energy, and it's lost to heat inside the resistor, heating it up, and some radiation is also pumped out in an inductor. So the total energy of the circuit over time, it's similar to damping that we've seen in the mass spring system. As the current moves through the inductor, we'll get a little bit of current back, we'll get a magnetic field induced, but we will also have heating and energy losses. And these equations really deal with how an inductor works. So here we're looking at the amount of energy that we're getting back from our inductor. And as you can see, it's a time-varying process. And this is the equation that really dictates it. This is the potential energy from the capacitor plus the potential energy we get from the inductor. So Q squared over 2C plus 1/2 over 1/2 Li squared. You don't really engage with this particular equation in this course. What I want you to do is get an idea of what an inductor does. We close this switch, the capacitor will give up its charge, it'll run through this inductor and give a little more current back. So you're not creating energy because there are losses due to heat. And a real RLC circuit comes from a time-varying magnetic field. So as the capacitor discharges, we've said it discharges over an exponential curve. So here's our Q starting off high and then moving down to low with time. That means we'll start to get some induction we'll start to get some current back from our inductor, and then as charge diminishes, our inductor slowly reduces in its energy output. And this becomes quite complicated quite quickly because you have exponential functions and you have cosine and sine functions for the harmonic nature of the variation in this field. And that's why we're not going to go too deeply into the actual mathematics of this case. But it was people like James Clerk Maxwell and Michael Faraday who did a lot of work into this, looking at electromagnetic induction, looking at electromagnetic waves, and figuring out that if you have a time-varying electric field when you're moving a current, you'll end up with a magnetic field coming back. And that means they discovered that electricity and magnetism are interrelated and slightly different facets of the same thing. A moving electric charge will give you a magnetic field. A changing magnetic field will move electric charge. And this was what Faraday and Maxwell basically did. It took a while later for Einstein to come up with general relativity, which explained this even more. It turns out if you see a charge moving, by the time you've spotted that charge, the magnetic field from that charge is someplace else, because the charge is moving so quickly. And you need to start looking at relativistic mathematics to truly understand this, which is not where we're going right now. So, what we're talking about is moving a charge through a wire and ending up with a magnetic field being produced. So any charge in motion, so any electrical current, will produce a magnetic field. The electric current is also an example of charges in motion. So here we have a charge moving through this wire. We have a current moving in the direction of this person's thumb. And this is one of the ways to envisage even mathematical magnetic fields. So here I is running this way. The current is going this way through the wire, and that means the magnetic field is going to curve around in this direction, B. Again, this is just switching the problem around. The current here is going downwards, which means the magnetic field here will curve around this direction. And the way to remember this is say, well, I'll point my thumb in the direction of the current and my fingers will curl around the direction of the magnetic field. And there's a slightly clearer version of those diagrams. And it's in this way that we can create an electromagnet. So over here we have magnets. Here's a north and a south pole for a permanent magnet, and magnetic fields very similarly to electric ones, which went positive, negative. Magnetic fields go from north to south, magnetic north to magnetic south. So they will curl around in this fashion. These are permanent magnets. These are magnetic materials such as iron, which have been deliberately magnetized. But if we create an inductor, a solenoid, so any curled around wire is referred to as a solenoid, we can actually create what's referred to as an electromagnet and simulate a bar magnet. So if you take a look at this magnetic field, it basically looks like that of a permanent magnet. So if we take our current and pass it through this inductor, pass it through this coil, any coil of wire will result in a magnetic field similar to that of a permanent magnet. Now, you can put a piece of metal in here and you can manipulate that through the magnetic field. Something else you can do, and this was what Faraday was doing, is take a coil which has no particular power source attached to it and then put a magnet into it. This V stands for velocity. So this magnet is moving through this coil. As long as the magnet is moving through the coil, that will cause this meter to register an actual current. The actual motion of the magnet through the coil will result in the electrons in the wire moving and creating a current. This is only going to happen while the magnet is in motion, hence the fact it says V. So while this magnet is being pushed into the coil, you will end up with a current being produced in the circuit. And this will happen either way. You could push the magnet in this way and you'll end up with a positive direction on this galvanometer over here. Pull it out and you'll register a current in the opposite direction. And if you wanted to end up with a bigger current, you could move this magnet faster. And that works with either a magnet, or you could do this with an electromagnet. The great thing about an electromagnet is if you want to swap the poles, you can simply switch these two wires around, as opposed to turning your magnet upside down. You can also have the opposite effect here, and you can change your output, change your magnetic field here by switching your system on and off. So here you've got an electric current going through this coil, and you can move this switch and you can generate electricity in both directions. So what does this mean for us? Well, we're going to discuss magnetic fields next time. But a changing magnetic field produces an electric field, and a changing electric field produces a magnetic field. So electricity and magnetism can produce forces on charges. An accelerating charge gives you electromagnetic radiation, will give you light. And this is what you're doing when you turn on a radio transmitter. You're bouncing electrons up and down at a specific frequency, and that's radiating energy at a specific frequency. So both electric and magnetic fields really transport energy, and that really is what light is. It's part of the electromagnetic spectrum. It's a mix of electricity and magnetism. So both E and M fields can transport energy, and the electric fields that's used in electrical circuits, such as lightning, will end up emitting energy and interfering with things like radio waves. Magnetic fields also carry energy through a transformer, which is something we'll get to shortly. And by transformer, we mean electrical transformer, not a robot that turns into a helicopter. So just finishing up here, ultimately electromagnetic radiation is interrelated electric and magnetic fields. So if you take a beam of light, it actually has an electric and a magnetic component to it. And all electromagnetic radiation, if it's in a vacuum, will travel at 299792458 meters per second, or about 3 times 10 to the 8 meters per second. And the way that light works was often a source of considerable debate in the late 1800s and early 1900s. For the longest time, people believed in a luminiferous ether, which was kind of the water version of waves here. So if you had, in the same way, a water wave is set up where you actually have to have a mechanical wave move through a medium. People felt that maybe that was the case, where light was a mechanical wave moving through space itself. And experiments couldn't define this luminiferous ether and find it. And this was a constant debate from Newton's period all the way up to Einstein. Eventually, when they decided to look at general relativity and look at the way that waves behave, it was determined that you don't actually need this ether. And electromagnetic waves are self-propagating. The magnetic component propagates the electric, and the electric propagates the magnetic. And they can move through empty space. So all of these things will be touched on later. We'll deal with electromagnetic radiation towards the end of the course, and of course we'll be dealing with magnetic fields next. And keep this idea of time-varying magnetic fields giving you a current, and time-varying currents giving you back a magnetic field. Take a look at RC circuits. Make sure you're familiar with which way the current will be going and which way the charge distribution will be going. Will charge be going up for a discharging case? No, it'll be going down, but so will currents. When you're looking at a charging case, of course, you're looking at charge increasing and current decreasing. So take a look at those things and make sure you've got those ideas down.